So today we're going to talk about acids and bases. This is part 4 of a multi-part video series on acids and bases. You can find the rest of these videos on my YouTube site, General Chemistry Talks with Dr. T. But today what we really want to focus on is just doing some calculations to figure out, theoretically anyway, what the pH is of a certain salt or material that you dissolve in water. And once again, kind of the focus here is that we're talking about acids and bases dissolved in water, and the other main focus here is that we're talking about individual substances alone, not how acids interact with bases together. It's just a single substance. One thing you need to be familiar with is the tables where you can get the important measures that tell you the acidity or basicity, and as we reviewed in a previous video, it's really the Ka that tells you whether something is strongly or weakly acidic or basic. And so I just want you to be familiar with using these tables. Here's an example of a table taken from Silverberg's book. This is Appendix C. But basically, if you look at the reaction of an acid, simplified, and remember once again the A in this symbol for an acid is not represent acid, it represents anion. So whenever this acid dissolves in water, it frees up the proton, which makes the solution acidic, and then it also frees up the anion. But if you're to refer to the table, and then if you set up the equilibrium expression, you might have a Ka or a K1, which is the dissociation expression. And I would point out that some of these refer to as K1, some of them refer to as Ka, and the point on the K1 is that sometimes you have polyprotic acids, so you'll release multiple protons. And here's an example of that. You can see it down here. Here's adipic acid, which has 2 protons that are acidic. And so the Ka for releasing the first proton is in this column, and the K2 for releasing the second proton is in this column. And always pay attention to these. And this is a unique example. These numbers are very fairly close to each other, but usually probably 90% of the time that second proton comes off a lot harder. With it's going to have a much lower Ka. The equilibrium is not going to favor it, because of once you remove one proton, you've left behind a negative area, and that is actually attractive to the proton leaving. So anyway, here's an expression for that polyprotic acid. So if we generalize it according to this HA, you would call this H2A. It disassociates into the monoprotic anion, and one of the protons is free. And then the second disassociation is over here when that second proton comes off. And so that is associated with the second disassociation constant. So just how to read these tables. By the same token, you can have tables that give you Kb for bases, which gives the base strength. Same sort of situation. I just generically use any base. I call it lowercase b, not to be confused with boron. Interacts with water, makes some sort of cation, and then it releases hydroxide. You could do an equilibrium constant expression for this. Once again, we'll usually refer to it as Kb, but sometimes you'll see it as Kb1 or K1, and what that's implying is there's multiple base sites. So if there's multiple base sites, here's ethylene diamine, and you'll see that there's actually 2 amine sites in here. So whenever you protonate the first site, that's the K1, and then when you deprotonate the second site, that's the K2. And finally, we had also mentioned that small, highly charged metallic ions, especially out of the transition metals and aluminum, these are slightly acidic. And so if you're trying to understand what the Ka is for those in particular, sometimes you'll see a Ka, a dissociation constant for free metal ions. Well, what that really implies is that you're basically looking at the metal already in some sort of hexo or tetrahydro form, and it's going to react with water and create protons just like this. Here's iron, for example, iron hexaquo complex. It's actually interacting with water and freeing up a proton. Or another way you could think about it is one of the waters that's attached releases a proton. And both of those are correct, but the point being, if you looked at the equilibrium for this, the expression would look like this, and really that is not that much different than if you look at the standard equation for an acid, where you start off with the acidic species, and when you get done it deprotonates and frees up one proton. So once again, the Ka is fairly much an expression very similar to most weak acids. How do you do calculations with acids and bases? I'm going to run you through this, and then we're going to do some practice problems, and that's really the objective here. So what's the pH of a 0.050 molar HCl solution? And the key on doing these sorts of problems is, first things first, you have to identify what the species is. Is it a strongly acidic? Is it strongly basic? Is it weakly acidic? Or is it weakly basic? Because that will determine how you solve the problem. And as an example, the first question we're asking about is a strongly acidic HCl solution. And once again, if you don't remember how to identify these, then please go back to video 3, which focuses on exactly that. Determining how to qualitatively just identify these as weak or strong. So today, once you've identified those, we can work on how you actually put numbers, how you quantify exactly what the pH of those is. So with that in mind, we look at this and we know, oh, this is a strong acid. So the way you work these is it's very straightforward. You just assume that it is completely disassociated. All right, and so if you have 0.050 molar HCl, you will free up 0.050 molar hydronium ions, and that makes the calculation fairly simple. Just to remind you that pH is found by the minus log of the hydronium ion concentration. Plug and chug, and you get a pH of 1.3. Now when you do the same sort of problem for a little bit more concentrated hydrofluoric acid, you remember back to your qualitative rules and say, oh, that's a weak acid, so it won't fully disassociate. So now how do you figure out what the pH is? So let's walk our way back through, and if you need to review equilibrium constants and working on that, this is how we're going to set that up. We're going to set this up in an ice table. But generally, you know, this is the same as all weak acids. They go through this general disassociation. If you set up an ice table, you say, well, initially I have 0.050 molar HA, or the hydrofluoric acid in this case, and the protons and the free anions for anything's disassociated is 0 molar in essence. The change is whatever amount disassociates from the HA is the amount of H plus, or hydronium ion, and anion that's formed. So at equilibrium, they're actually going to be at these concentrations. And if you set that up into the equilibrium constant, and you know that the equilibrium constant is the Ka, and you can plug in the x and the 0.5 minus x, but then remember the approximation. If you'll divide the concentration by the equilibrium constant, and if that number is greater than 400, as it is here, you can do the approximation that for the amount of change of x that's insignificant to the concentration in the starting material. So you can estimate that at 0.5. Makes your math a lot easier. And in essence, you're looking at this to solve for x, right? You bring the 0.5 over, multiply it by the equilibrium constant, take the square root, that would solve for x, and when you work that out, you end up with 0.018 molar, which is the concentration of hydronium ion and the concentration of the anion. If I want to do the pH, you take the minus log of that concentration, so you get a pH of 1.7. So a few key points here. It's a weak acid, so we assume it's going to be a lot less than fully dissociated. So we start at 0.5 molar. We ended up at 0.018 molar, so that makes sense. All right? And if you just take this form, for most weak acids, right, they usually disassociate one proton. You can usually make the approximation that the amount that you're losing is insignificant compared to the amount of quantity you're starting with. So this general form of the equation, you could rewrite it just like this, and basically say if you ever want to find the H plus concentration of any weak acid, it's going to be the square root of the acid dissociation constant times the initial concentration, and that's a go-to equation. The only catch is pay attention that the concentration isn't too low, right? Because this approximation needs to hold. So this concentration, if this gets low enough, you may not break 400. And the other thing is that the Ka isn't too high. And that is the definition of a weak acid, that the Ka isn't high. So that's usually safe. So we're just going to block this out. This is an equation you should memorize and get used to using. And I'll show you that in the homework problems we're going to do here in a minute. Here's another problem. Now once again, this is using that highly charged small transition metal, so we know it's going to be weakly acidic. First thing is identify what this is. Weak, strong, acid, base, that's important. So we know it's a weak acid. Where do you find the Ka? Well, as I showed you earlier, there was a table. You could look that up. And the Ka for the hexa-aqua complex is 6.0 times 10 to the minus 3. Consequently, when you look at this form of the equation, very similar to this. So you work it the same way. And as I just showed you, the go-to equation for that is really the H plus concentration is the Ka times the original concentration. Take the square root. Well, here's the original concentration. Here's the Ka. So you plug and chug and solve. You get 0.17 molar. Take the negative log of that, and you get 0.76. All right, so now we're going to go to the next problem and identify this right away. Okay, here's a nitrogen with 1, 2, 3 bonds. That makes it weakly basic. All right, so you set it up. If you set up the equation for it, and then you set up an ice table for that, I'm just going to walk you through this first one so you can kind of see the pattern. Initial concentration is 0.50 molar. These are 0 and 0. The amount it changes is x. So at equilibrium, it's 0.5 minus x. These are all increased by x. You set that into an equilibrium expression. As we showed you generically for all the bases disassociating, it'll look very much like this. Plug and chug. Here's the Kb, which we got. The x squared over, and now remember again, you can use this approximation if you take the original concentration by the Kb and it's greater than 400, which usually will hold. Once again, that is the definition of a weak base. And you can solve for x, which is also the hydroxide ion concentration. It's 0.017. I go ahead and just solve for the pOH of that quickly because it's minus log of that number. I can put it on my calculator quickly. I get 1.8. I remember back to earlier videos where I could take pOH and turn it to pH by subtracting it from 14. I get 12.2, and that's the answer. And once again, if you'll look at this generic equation, the hydroxide ion concentration for a weak base is the Kb times the original base concentration. There's your go-to equation. Very similar in structure to the hydronium ion concentration for a weak acid dissociation. So you should memorize these two forms of the equation. All right, here's a slight variation. What is the pH of 5 molar sodium acetate? We go back and identify this qualitatively first. It's the conjugate base of a weak acid, so it's a weak base is actually what this is. So I need the Kb, but if you look in your tables, you're not going to find a Kb for an acetate. What you're going to find is the Ka for acetic acid. So that also asks you to look back and say, okay, how do I get from a Ka to the Kb for a conjugate acid-base pair? And you remember that what you do is divide 1 times 10 to the minus 14, which is the Kw for water, right? Divide it by your Ka, and that'll be the Kb, which is 5.6 times 10 to the minus 10. All right. Then if you look at this equilibrium expression, now we can fall right back on what we just learned. Plug and chug, 5.6 times 10 to the minus 10 times the original base concentration, which was 5 molar. Solve, you get 5.3 times 10 to the minus 5th. That's the OH concentration. I quickly solve for the POH. Now remember, you can do this different ways. You could also divide it into 1 times 10 to the minus 14th and get the H plus concentration. You can go in that direction or go this direction. Either way, you solve for POH, subtract from pH, you get 9.7. Now if you go the opposite direction, it might be slightly off by 1/10, but remember within the significant figures of this, this is plus or minus 0.2 at least. So now what about polyprotic acids? Now we're going to do the pH of carbonic acid. So this is a polyprotic acid, so it can lose 2 protons. So how do we figure out the concentration? So let's just take it one step at a time. Let's first off write the overall equation. Carbonic acid deprotonates once, becomes hydrogen carbonate anion, and one of the protons is free. It deprotonates again and becomes a carbonate anion with the second proton. So the first question I think you should consider is which one of these protons is really influential to the overall, remember we just dropped this in water and this shifts somewhere along this equilibrium. Where's it going to be favored? And the key is that look at the K1, it's to the negative 7. Look at K2, it's to the negative 11. So this has much more influence over this. So the bulk of the chemistry happens right here with slight amount of movement over to the carbonate. Okay, and that's because of how the K1 compares to the K2. And it's important that you look at tables, because if you'll scan through the tables of your polyprotic acids, what you'll see is that 90% of the time this is the trend that holds, is that first proton comes off with a much lower equilibrium constant than the second proton coming off. Okay, and that makes sense because of the buildup of anionic charge. Once you've lost the first proton, makes it harder to lose the second proton. So the go-to equation for that first deprotonation is right here, as we talked about earlier. Only for Ka, you're plugging in the K1, right? And you're talking about the original diprotonated form, what that concentration is. You can basically plug, you're plugging in 4.5 and you're plugging in a 0.5 in for the original concentration. You solve, you get 4.7 times 10 to the minus 4th. That, by the way, also is the hydrogen carbonate concentration as well. But if you were to solve for this, that would give you the proton concentration that really determines the pH. You take the minus log of that, you get 3.3. But just understand, so what about moving on? What happens in the next step? Well, K2, all right, that's determined by the actual proton concentration times the carbonate concentration, right? The products divided by the hydrogen carbonate. But now, if you'll remember though, we just solved that this is the most predominant equilibrium constant, so it drives the show. So when we go to plug in here, really the proton concentration is not determined by what shows up on that second deprotonation. It's already present from the first, so we plug that number back in there. That also is the number that goes in for the hydrogen carbonate. And you could see how generically this would be true of any deprotonation of a polyprotic acid. And when you solve these always cancel. So consequently, the K2 is actually what this deprotonated carbonate anion concentration is. And that's not a coincidence. That tends to happen most every time. So here's a kind of a generic way to think about polyprotic acids. Okay? The K1 determines the pH. And the K2 is always equal to the concentration of the deprotonated anion, right? So there's kind of your go-to formula. And to solve the pH, you basically just use the K1 and the original polyprotic acid concentration, and you can solve and derive the pH. Alright, so you'll get some practice on that. So now we've tried all these different, kind of looked at these situations where you're looking at strong acid, weak acid, the conjugate acid or the conjugate base from an acid or base form, and then you plug and chug. And keep in mind also that strong acids or strong bases directly determine the concentration of the H plus or the OH minus respectively. So now I have a table, and this is going to give you lots of work, and what I'd like for you to do is basically, pause your video, work on these problems. Now as I work through some of these problems, I'm not going to stop and take as much detail to work every part of it. You can review the other slides right before this one to see how I did these problems. And the other advice I'd have for you is stop your video, work these problems out, see what you can get done. If there's a problem you come to and you can't work out the solution, then move to the next row and see if you can solve that problem. And the other thing I would point out here is this is just going to give you a lot of repetitions and exercise doing a lot of things. So we're not just going to solve for the H, we're always going to solve for the pH, the OH minus, and the POH in water. Assume that every one of these species is dropped into water at this concentration. Okay? And then the other thing is if it's a polyprotic like the sulfurous acid down here, if it's some other species where I think it's important that you know how to find some of the anions that are created farther down the equilibrium to the right, then I'll also solve for these, and this will just be good practice for you. So see how much of this you can fill out. Okay, so let's work our way through. And remember, the first step here is identify qualitatively what the species is you're looking at, because that'll determine how you have to solve the problem. So the first species is a strong base, so I certainly don't need a constant for this because it's going to fully disassociate. And it's a base, so it fully disassociates into hydroxide, so 0.20 molar sodium hydroxide will give me 0.20 molar hydroxide. That will determine the POH. That's easy enough, minus log of OH. That then in turn could tell me the pH, subtract it from 14, and then I can work that back to the H plus concentration. Remember, raise the negative pH to the power of base 10, and you'll end up with the H plus concentration. Problem solved. All right, let's work on to the next one. Identify this right away. It's aluminum, very small. It's an aluminum 3 plus, highly charged. The nitrate in this case is the conjugate base of a very strong acid, so it's neutral. So aluminum plus 3 is slightly acidic. And the Ka for that is 1 times 10 to the minus 5. So I use that generic formula that'll give me the H plus concentration. I worked that out at 6.7 e to the minus 4. Find the pH. Key off that to work over to the OH minus, which you can do that, divide this into 1 times 10 to the minus 14. Or if you want, you can work it the other way and subtract this from 14. And away we go. So here's sulfurous acid. It's H2SO3, not SO4. So this is a weak acid. So once again, as we just learned, the K1 runs the show. So we can use the generic H plus equation to figure out what the concentration is going to be using this K1, and this original concentration ends up being 0.30 molar. That's the key to the pH, which then just chains down, figures out the POH, subtract that from 14, work that back to OH minus concentration if you'd like, raise the negative POH to the power of base 10, you get 3.2 times 10 to the minus 14th. And just for grins here, what we might do is we might solve farther down the line. Whenever you do this first dissociation, the H plus concentration is also the HSO3, the hydrogen sulfite concentration. So that also is 0.3. All right. And then if you'll take these, and remember what we learned in the last video about polyprotic acids, that really, when you work it out, the sulfite concentration is going to be equal to the K2. All right, and you can work back on that last slide and see how that works. So now we come to the carbonate anion. We know that it is the conjugate base of a very weak acid, carbonic acid. So now what we need is the Kb for this, but all we've got apparently is, and this would make sense, that really you're going to only have the Ka for that carbonic acid, and you need to choose the one that actually is the Ka that's associated with turning it to carbonate, which is the K2 when you deprotonate the second proton, so it's this number. And remember, if you take that into the Kw of water, you can solve for the Kb, and that's the number I need to solve out the basicity using the generic form original concentration times the Kb, and I'll get 5.2 times 10 to the minus 3. Go ahead and solve the POH. And while we're at it, I might just add that if that's the OH concentration, working from carbonate back, that also is the hydrogen carbonate concentration, just in case you're wondering. But now that I know the OH minus, I can solve the POH. I can key that back to pH. I can key that back to H plus, and away we go. Okay, the next species, we know that this is nitrogen bound to three things. It's a weak base. We know the Kb, the original concentration. It's from there it's easy enough to solve the OH minus concentration, which keys me to the POH, which keys me back to the pH, which keys me back to the H plus. All right, and just a reminder that if ammonia is protonated as a base, it's an ammonium ion. The concentration of that is equal to the proton or the OH that's created. All right, just a little reminder if you had to find that. So now we're talking about acetic acid. This is an organic acid. We know that's a weak acid. We have the original concentration. We have the Ka. We just use the generic formula, solve the H plus, keys me to the pH, which keys me to the POH, which keys me to the OH concentration. So the last species is ammonium chloride. Is nitrogen bound to four things, so we know that it's actually a weak acid. And the chloride ion is actually a neutral anion, so it doesn't contribute to the acidity or basicity. But ammonium, we're not going to have a Ka for that, but we are going to have the pKb for the ammonia ion, which is right here. We can use it as a conjugate and figure out its Ka, 5.9 times 10 to the minus 3. And now you're off to the races. You have the original concentration, you have the Ka, solve for the H plus, which will lead you to the pH. pH can lead you to the POH, and from the POH you can solve for the OH minus concentration. So this is a good set of exercises, and you should run through it again. But I hope this has helped you to figure out how to quantitatively figure out the pH of different species of strong acids, weak acids, strong bases, weak bases when they're dropped in water.